So we can continue. So now, given this new parameterization of the string vertices which I've just introduced, that is in terms of these string products L, let me finally write this thing is an important form of the action for the closed string field theory. And that is the kinetic geometry, or the new from the last time. That's now the interactions which can be rewritten to recalling the right symmetry factors which went into the definition of these string products. Suppose so with this wedge n, what I mean is that I'm taking n copies of this phi, and this wedge emphasizes the fact that Ln, the products Ln, are totally graded symmetric in the insertions of this string field phi. So then, of course, we remember that the original free action phi q phi was enjoying a symmetry under gauge transformation. So now, of course, if you just try and vary this action with respect to phi and substitute this gauge symmetry q lambda, that interacting action is no longer invariant under that simple gauge transformation. But there is a corresponding generalization. So using the L infinity property, using the L infinity relation satisfied by these products L, you can prove that is a nice exercise, that the action is invariant under this interacting gauge transformation. So string field theory, even at the interacting level, continues to be a gauge theory in space-time. So let me now make a couple of remarks and a couple of illustrations. What I have introduced was very abstract. So I think it helps to illustrate especially the logic behind these infinity relations on some simple examples. Before I come to that, let me point out a couple of things. First of all, notice the degree of these products L, right? So we know that the string field phi, which goes into the action, is a state in the string Hilbert space, which is degree 2, in particular degree even, right? Right. So then last time we saw that omega has to have degree minus phi, and q has degree plus 1, right? So that means that in order, everything to be homogeneous in the degree, that means that these guys L, the same as Q, they have to have odd degree, okay? So the of L is odd. So that's one thing. Now the other thing, as I was pointing out a couple of times already, there was a huge freedom in making the choice of these vertices and correspondingly in making the choice of these products L. Right? So then you might worry, okay, SFT action, okay, it's a concept which is heavily unique, but this is precisely as it should be, right? Because at the level of the action, we are always free to make a future definition, right? And it can be proved. So for the formal way of proving, see the notes of Ashoksen and Martin-Zwiebach. It can be proved that this freedom in choice of the vertex regions is precisely in one-to-one correspondence with the future definitions. Of the string fields. So this just adds to the overall consistency of the SFT action. Second thing, you might have noticed that in writing down the original expression for the off-shell string amplitude, I've omitted a factor of G string, right? So we know that in order to be able to recover the correct answer for the on-shell amplitude in particular, each expression for these amplitudes A0n needs to come with a specific power of G string, and that will then proliferate through the computation, and there will be specific powers of G string in front of the interaction vertices in that action. So I was omitting these factors of G string just to reduce clutter. But they will be there, and in particular, those interactions can then be really formally set to 0 by setting G string to 0, because these powers of G strings here will be positive, right? So that nicely corresponds with the intuition that as soon as we set G string to 0, we should reduce back to the free theory. Okay, so we have omitted G string. Now, third, this is of course, the defining expression for the L-infinity relations, which is at the same time the defining relation for these string products. That is a complicated algebraic relation, right? So in order to illustrate it, let me notice that L-infinity algebra is just a generalization of a simple differential graded Lie algebra.
Just about G string, can you just shift the G string? I guess I was kind of asking you this last time. Can you shift the G string by changing phi, the part of phi that corresponds to the dilaton?
Yes. Yeah. So that is one thing which you can do in string field theory. You can construct a classical solution, which is going to be a marginal deformation initiated by a special universal state in the Hilbert space, which we call the ghost dilaton. And that renormalizes the value of the G string in front of the vertices. Okay. So back to what I was talking about. So in particular, you can make the following choice of these products. So L1 is just a different name for Q. Okay, I can call it L1 because it is a one product. It is an operator on the Hilbert space taking one state and giving you another state. So if we take this L1 to be just a differential on some graded vector space, and if you take L2 to be up to sine just a Lie bracket. This is a two bracket. It's an operator which it's a product which takes you from two copies of your space to a single copy. And if you set all these L3, L4, etc. to 0, then the first couple of L-infinity relations which you obtain, by fixing the value of n, precisely give you the algebra of the relations of the differential graded Lie algebra. So in particular, if you set n equal 1 in that relation up there, that just amounts to saying that the BRST charge, or in this case the differential, is nilpotent, right? And if you set n equal to 2, you will obtain a relation which is saying that this differential should act as a derivation on this Lie bracket. And first, if you set n equal to 3 in these L-infinity relations, you will just obtain the Jacobi identity for this two bracket. So that's nice. But at the same time, this tells you more reliable than L-infinity algebra is. So in the cases where this third relation, this third relation would have been completed in the case that L3, the free bracket, would not be equal to 0 by other contributions, right? So these contributions arise precisely in the case where this 2 bracket L2 fails to satisfy the Jacobi identity, and in particular, if the failure of this Jacobi identity is, so as to speak, up to homotopy, that is, if you can write it as a differential acting on some free bracket, A1, A2, A3, and then of course minus, and then all the terms where the differential acts inside. Again, up to signs. Then this would then this would give you precisely that L-infinity relation in the case of n equal 3, and so on, right? So because then when this free bracket is no longer is no longer trivial, then there will be a non-trivial relation for n equal 4, which in the case of just the differentiability algebra would be just 0 equal 0. Okay. So yeah, I hope that illustrates a little bit what an L-infinity algebra is and what it does. So then I had then originally I was intended to also make some comments about what happens at a quantum level, because what we've done so far was a construction of a 3-level classical action. But then in the interest of time, let me completely skip the quantum story, because we will no longer need it in the applications to IPHT. So then let me go directly to comment number 5. And that is, of course, so far, what I've given you is just a set of algebraic relation which these string vertices or the string product need to satisfy in order for the SFT to correctly compute the amplitudes, right? But at the same time, I was trying to sketch a recursive procedure which in principle would allow you to construct these vertices, but I didn't give you any particular form or any particular solution to these equations. And indeed, these equations are very, very hard to solve, and they turn out to be actually so hard to solve that in the closed string case, even up to this date, I mean, even up to 40 years after the conception of string field theory, we don't really have explicit forms for generic B0n vertex. So in the case of closed string, the concrete forms of examples of string vertices and generic number of functions are still missing. So what we do have at our disposal are some concrete results only for at low orders. So we have examples for n equal 3, n equal 4, but then depending on what you want to compute, you can also construct some higher point vertices which will work for some special states, for instance for states which are on shell or close to on shell, but not for generic states. So in particular, as you will see, that is good enough for us to do some order perturbative calculations, but not really enough for us to, let's say, construct some solutions which we expect to be deeply non-perturbative, like the tachyon vacuum of the closed string field theory. So that's the situation in the closed string field theory. On the other hand, in the open string field theory, the situation is much more. Yes.
So before we depart from closed to open,
yes.
Can you just summarize like what it would take to get that information?
Yes. So So exactly. I mean, we would need to go and recursively solve this equation, right? So we need to, I mean, each of these vertices v0 we need to parameterize it with some data, right? So we need to parameterize it with this choice of local coordinates, and then you know, solve for these local coordinates in such a way so as to satisfy this recurrent equation, right? So that in general will boil down to solving some differential equations for these maps Fi, which I was showing, right? And yeah, these are hard to solve in general.
But from the point of view of other approaches to string theory, is there some set of computations one could do to then port over to this setting?
Okay, I'm not sure I understand.
I'm sure it's I who doesn't understand, but I'm just kind of grasping for why, more about the why there's this void in what is known here from other points of view on string theory.
Okay, it would be, yeah, okay. I'm not sure what other points of view of string theory would be, at least, roughly equivalent to the point of view which string field theory is trying to take, right? I mean, string field theory is trying to be an off-shell field formulation for strings. So, I mean, if there is something analogous which I can compare to, then perhaps I can answer the question. But
well, presumably, like string perturbation theory, for the on-shell states, the usual one gives some constraints on these maps. No?
Yeah, but for the on-shell states, I mean, I don't have to worry about the local coordinates, and which are which is the principal source of all these complications, right? I mean, these are the objects which I have to solve for. Yeah, I mean, going off shell turns out to be difficult. That's what I can say.
Even if you just want to, is there not some like other infinite set of on-shell string perturbative data that could be used to, say, write the n equals 4? If you just fix some low n, you want to.
Yeah. I mean, at each fixed n, you have to solve a finite number of equations, right? Those equations are hard, and I mean, as n goes higher and higher, I mean, you have to solve a higher and higher number of hard equations, right? So that's
yeah. So let's not go higher. Let's just say take n equals 4.
Yes.
Like. It's not. I'm trying. I guess I'm asking whether it is like understood in principle how one could use data obtained by other means to solve those equations, and if there is no such answer, then it's a little bit one is pretty boxed in. I mean,
well,
yeah. Like,
okay, I'll try.
The state of the field seems grim if that's the case, right?
Well, no, there are various strategies to solve for these vertices. There is there are special classes of there are various approaches which may give you some hope. So there is this approach of trying to solve for these vertices. I mean, in the realm of hyperbolic spaces. So that was initiated by Costello and Zwieback. So, but even there, even using this ansatz of hyperbolic vertices at each order, you have to solve some some complicated differential equations. So, yeah, there are various approaches. So there is the minimal area approach by Barton Zwieback, which is analogous to what is. I mean, that is aiming to be a generalization of the written cubic vertex in the open string, which I was just going to talk about. Yeah, but.
Is there no, just to try to boil this down to something simple, like, is there no even a principal prescription for some more traditional on-shell string computation But if you could do it, would allow you to determine the n equals 4 case?
Yeah, so you're asking if it is, I mean, if just by knowing the on-shell answer, if it is enough to generalize completely.
So you need some like huge set of on-shell data, like is it known which data you would need to use to then write this down?
Yeah, that I think is a good question. Okay, I don't have an immediate answer, but I mean, yeah, assuming that you have an infinite knowledge of all possible on-shell amplitudes, I mean, how much you can learn about the off-shell vertex. I don't know, but yeah, perhaps this is something which might turn out to be a good approach.
So you're saying that not even V4 is known for generality?
It is. It is included in this. Yeah.
V3 and V4 are known completely for all the string theories.
For the co-string. Yeah. I mean this.
Bosonic and superstring.
Yeah, I mean, as soon as you know the answer for bosonic, I mean, the superstring construction. I mean, there is a construction, or there are various constructions which just by taking the bosonic input, I mean, they tell you how to distribute the PCOs over the insertions in order to get a correct superstring amplitude. Yeah. Okay. So in OpenSFT, we can actually draw a smiley face because we have a complete action. Because in OpenSFT we happen to be very, very lucky and show that there is a choice of the cubic vertex which already covers the complete moduli space. I mean, the cubic vertex plus propagators. With that, we can cover the complete moduli space of any off-shell amplitude at any number of functors, of open string functors. I wrote it. And that is the written cubic OSFT.
Is there a simple conceptual reason why it works for the open string and not for a closed string?
Yeah.
Some kind of proof with pictures of Riemann surfaces and so on. Okay.
Yeah. Okay. My intuition for this is that it fails in the case of the co-string due to the requirement of the level matching. That whatever output these products, I mean, the outputs of these products out, they contain an implicit projector on the V0 minus exact states, right? So even if I try and write down an analog of just taking a homomorphic and anti-homomorphic part of the Witten's vertex for the co-string, right? That is no longer associated as it would have been for the open string because of these projectors on the level match states. So, having mentioned this Witten's open string field theory, let me just give you a final remark before I move to giving some examples of classical solutions. And that is precisely how this story will generalize in the case of classical open string field theory. Like by the story, I mean the story which I was telling you so far for the case of pure closed string. So here, I'm changing the gears a little bit. Instead of discussing off-shell amplitudes on Riemann spheres with functors, I will just sketch what the situation is in the case of off-shell amplitudes on disks. With boundary functors. So again, the integrands, this time are going to be disks, where the open string states are now inserted on the boundary. And again, I would have been making a choice of the focal coordinates around each of these functions, right? Where this time I will be mapping this kind of a half disk region to a unit half disk in each of the local coordinates. So this is a Z disk, and this is WI, and this is I, this is O. Okay. So that would be an analogous picture to what I was drawing in the ghost-string case. So that would be the integrand. And then, of course, I will take this integrand, I will insert some bghost contours and integrate over the respective section of a fiber bond on the moduli space. So now why I'm drawing this picture is, this is mainly to emphasize one fact. So while I was having a total graded symmetry requirement for the ghost string of shell amplitudes, here, of course, I cannot generate active global conformal transformation to completely permute these boundary insertions. Whatever I do, I need to preserve the cyclic ordering, right? So the vertices of the open string field theory, the interacting vertices which enter the action of the open string field theory, will no longer be totally graded symmetric, but they will be just totally graded cyclic. So then the action can be written as follows. In general, where for the open string vertices I have introduced another set of string products which take you from the n copies of the open string Hilbert space to and give you another state in the open string Hilbert space. But now there is no requirement on the graded symmetry of these products M. There is the only requirement which the only restriction which I am putting is that these products that are graded cyclic with respect to this non-degenerate bilinear form, which gives us these open string vertices. So these open string products Mn are just graded cyclic. And completely parallel to the ghost string case, the requirement that the Feynman rules constructed from this action give us precisely the open string of shell amplitudes with no gaps and no overcounting of when we integrate over this section on the moduli space. So that requirement is precisely equivalent to what we call the A infinity relations for these products M. So again, we would act with Q on all the insertions inside this product N. And then on the right hand side, you get all the possible nestings of higher order products. So sum equal to 2 and minus 1. There will be some insertions inside, and then also some insertions behind, and then finally we would close off the finite. Okay? So that is the corresponding algebra of the string products in the open string case. So now, as I was saying, in the open string story, we are lucky enough to have a theory which is just cubic. So that amounts to saying that there is a theory, the Witten's OSFT, in which I can set M3 to equal to 0, M4 to equal to 0, etc. Right? So if you think about what this amounts to when you expand these infinite relations for n equal 1, 2, and 3, again that amounts to saying that the BRST charge, the kinetic operator, is not potent as it should be, right? Then the second infinite relation tells you that the two product, this M2, which gives you the cubic vertex, that Q acts as a derivation of this M2. So schematically, that can be written as saying that Q commutes with M2. So this is saying that when I act on the output of M2, it is as good as saying as acting with Q on the inputs. So Q is derivation of M2. And then finally, the analog of the Jacobi identity, which I had for the differential graded Lie algebra, here is the property that this product M2 is associative, which schematically I write as follows. Right? And again, the favor of associativity would have been parameterized by adding a product M3. But that is not necessary if I choose my open string field theory to be of this Witten type.
Can we define string theory to be an A? Can we define open string theory to be an A infinite algebra, or is the inclusion strict? Any string theory gives you an A infinite algebra.
Any string theory, any open string theory gives you an infinite algebra. Of course, I mean, in order to completely specify an infinite algebra, I first of all need to specify the Hilbert space on which these products act, right? So
yeah, so you need to specify this omega or something.
Yeah, the Hilbert space, the simple. I mean, yeah, if I want to specify whether the products, whether the A infinite algebra is cyclic or not, I need to also specify the omega. But I do about just these relations that they do not know about omega actually, right?
Okay, but is there some kind of like an algebraic definition that's believed to be complete, that once you have a Hilbert space with omega, with these m's or l's, then that's a string theory?
Yes. Yeah. I mean, if I give you the open string Hilbert space, so you know on what states these act. I mean, if I give you a background, right, and the string states on the background, and you are able to give me back, a set of products and which satisfy these relations. I mean, that is as good as defining an SFT, right? Because I mean, these steps which I was showing you before, that was a chain of equivalences. So you giving me an infinite algebra is as good as you giving me a suitable decomposition of the section of the moduli space, right?
So the statement is within OSFT is that like around any background you have this, or what exactly is the statement? That if so you start with some background and you use this within OSFT.
Yeah.
But
So
you go to some other background.
Yeah. So I'm actually coming to this. I wanted to start discussing classical solutions, which is probably what you're referring to, right?
I guess to add to Dalinol's question
Yes.
from before, does any A infinity algebra give a consistent string? I guess that was your question. Give a consistent string field theory, or are there kind of interesting constraints coming from the fact that on-shell amplitudes have to be reproduced?
But if your vertices satisfy infinite algebra, then I think it's automatic.
No, we don't know what you want to classify string. I mean, there are different string theories, and they're going to have different amplitudes, and you want to know what is the space of all string theories.
That
so.
makes sense. Okay, that's a fair answer.
Maybe there are some string theories that haven't been discovered because people haven't classified these algebras. I don't know.
I mean, yeah, the statement is, I mean, whatever Okay, it depends on what you call like separate or non-equivalent algebras, right? I would say that if you know, two different sets of infinite algebras are equivalent under field theory definition at the level of the action, I mean they should in a way be you know, call the same infinite algebra.
Do we have any idea of what, like, is this notion of equivalence sort of well understood, or from the algebraic point of view?
I'm not sure. I know the answer. I'm not such a big expert in this algebraic formulation of SAT. I can think about this. So
there's some in this discussion of, well, maybe this is best suited for the when we transition to the 2D CFT part next time, but let's see. In this classification question of string theories, is there some purely is there some purely 2D CFT language one could use?
Purely 2D CFT. Yeah, I think the answer is unfortunately no, and that's I think it's both a bug and a feature. I mean it's a bug in the sense that it would be very nice to have like pure 2D CFT formulation of what we do. I mean perhaps this thing which we call the boundary string field theory goes into that direction, or the background independent string field theory, people sometimes call it. So that is a formulation of SFT which is very, very similar to conformal perturbation theory, right? But yeah, that formulation has many problems, I would say. So yeah, so on the other hand, the 2D, I mean, this kind of even at the level of the Witten-Solé SFT, as you will see next time, it is far from obvious that what we are doing is somewhat equivalent to conformal perturbation theory, right? But then again, you will see that you know, trying to answer questions in conformal perturbation theory using Witten-Solé SFT, I mean, gives you a completely different language, which in many ways gives you, many situations gives you a huge advantage. So we will see that the computation which in conformal perturbation theory, I mean, is done at 3 pages, will be done using Witten-Solé SFT in 3 lines. So that's, but the price you have to pay that it obscures the pure 2D CFT data. Perhaps just to you know, make things clear. I mean, in all what we've done here, I mean, we had to specify the consistent string backgrounds we were starting with, right? I mean, choosing different products and is not in any way connected in choosing or classify different string backgrounds. The string background for the given SFT was fixed at the beginning, right? And different choices of ends should correspond to future definitions, not, you know, going to different backgrounds, right? So what Honesty implements, you know, looking for different backgrounds starting from a given background are the classical solutions. So in the conventional first quantized, you know, string worksheet perturbation theory, we usually have like no choice but to just work with the background which we specify, right? Given the background, we can compute all the observables on show data, on show amplitudes, blah blah blah, right? But then in SFT, and yeah, that's one of the advantages which I was mentioning in the first lecture, we can do more, right? We can take the SFT action as a variation principle. We can derive the corresponding equation of motion. And then the claim is that the field configurations phi star, which are solutions to this equation of motion, of course after gauge transformations, should be interpreted as giving you different and in general non-perturbative backgrounds for classical string. Right. So you can do this exercise for the sake of definiteness, I've chosen this L-infinitive form of the action, that is the closed string. And upon varying this action, you can derive that these are the equations of motion. Again, you can just do a sanity check, and let's say we set G string to 0, so that should be as good as forgetting about these string products, and what we get is the equation of motion, which we got in the first lecture, right, which is just imposing the on-shell lens. So then the statement is that the solutions phi star should be in one-to-one correspondence with consistent string grounds. So now, of course, just to do yet another sanity check, we have started with a consistent string background, right? So the trivial solution, so the trivial field configuration of phi star equals 0 should be a solution. And since these products are linear and they start with n equal 2, you can see that phi star equals 0 is indeed a solution. And that is connected with the fact that in this original action which we are varying, there was no tadpole, right? So that tadpole would have corresponded to an off-shell, a 1-point amplitude, which, I mean, if we reduce it to on-shell, I mean, it would have to give us an on-shell 1-point amplitude, but these things are known to vanish for a consistent string background, at least at a classical level. Of course, at a quantum level, the vacuum can get corrected, as I was trying to explain in the first lecture, and then phi star equals 0 is no longer a solution, and we have to do vacuum shifts. So then let's try and elucidate a little bit the statement that the classical field configuration phi star should correspond to other string backgrounds. So in particular, what we can do, we can take this field configuration phi star and expand in small fluctuations around it. So that in principle, if we substitute this expansion in small fluctuation into the original action, that should give us a new action for the fluctuation, which should give us the physics of this background, this would-be background, which correspond to this classical solution. And if this is to be a consistent string background, that new action would better be a consistent SFT action, right? So let's see if we can get this. So the strategy now is to take the original string field phi and expand it in small fluctuations around this classical field configuration phi star. Okay. And substitute this expanded string field into the original action. So that defines a new action for this fluctuation order phi, which I will call order S. So by definition, this is capital S, capital phi star plus lowercase phi. So now let's see what we get, right? So first of all, what we get is just a constant, which is the on-shell value of the original action, right? So let me actually make some comments about this on-shell value later. But now let me continue in the expansion procedure, so as not to lose momentum. So first of all, what we get is something which would be a tadpole, right? So this tadpole, I can represent it again with a string product, this time a zero string product, which takes 0 inputs and gives you 1 output, right? But if you really expand this action, you can of course explicitly derive what this tadpole is, right? And that tadpole turns out to be nothing but the equation of motion for this capital phi star. So this is good, right? This is saying that if the configuration around which we're expanding, and I think it's something which is more or less obvious, if the configuration around which we're expanding is a classical solution, that corresponds to saying that the expanded action will have a vanishing tadpole. Okay? So then we can continue. And we can construct the kinetic term of the expanded action. So that will come with some expanded BRST charge, shifted BRST charge little q, where this little q can again be defined in terms of the action of this little q on the fluctuation phi can be defined in terms of the action of the original BRST charge capital Q and the classical solution, right? So again, after you do your algebra, the answer that you obtain is the following. So then, this is to be, the expanded action is to be a consistent string field theory, that new operator little q would better be nilpotent, right? So then, okay, again, in view of time, I give it to you as an exercise to show that as a consequence of these original string product capital and satisfying the L infinity relations, and also as a consequence of this phi star satisfying the equation of motion, we can show that this is indeed the case, that q squared is equal to 0. Those equations of motion. Okay, and then you can continue. You can, in a similar way, you can define all the higher interacting vertices, or compute actually the higher interacting vertices of this expanded action. I will not write down an explicit expression for these, okay, but the story is then precisely what you would have expected based on what you got for this Q. Again, as a consequence of the L infinity relation satisfied by these products capital L, and also as a consequence of the equations of motion for phi star, you can show that these products little l, they satisfy L infinity relations.
If you start from the Witten's cubic
Yes.
one and you go to some different background,
Yes.
then can you make a field redefinition in these little phi's to bring it back to the Witten's cubic form? Or?
Actually, you don't even have to. I don't think you even have to. Have to make a. Okay, I will have to think about this if this property preserves associated with of M2. Yeah, perhaps we can do this computation after the lecture. Sorry, I think that should be something which I should know and which should be obvious, but yeah, I'm just not sure at the moment. But certainly there should. I mean, if it turns out to be not to be associative, the shifted product, and we should be able to make a future definition to make it associated. Yeah.
What does associative have to do with my question?
Well, Witten sphere being cubing is
the same
equivalent to
thing
M2 being
okay.
associated.
I see.
Okay.
So if it's associative, then there's a field redefinition which brings it back, which brings it to the.
I think, yeah, I mean certainly there should be, right? But yeah, let's see. Yeah. So this series of statements which I just made, I mean, should hopefully elucidate in what way the classical solution should be thought of as different consistent backgrounds for string theory. And then okay, equivalent to the statement is also saying that this action little s, which I was writing down as an expansion in terms of these small fluctuations, should be thought of as the SFD or SA, actually as a string field pair around the new background up to future definition. So then, in order to find some properties of these backgrounds associated with the solution phi star, and in order to either to match them to something which we know, or in order to identify properties of some new backgrounds which might be discovered in this way, we of course need to know how to compute observables, right, associated with this phi star. And using this new expanded action little s of little phi, I mean, that can be done, right? We can, for instance, take this new BRST operator with a Q and use it to compute the spectrum of on-shell physical string states around the new background by determining or by computing the cohomology. So Q is completely determined in terms of the original Q, in terms of the original string product, and in terms of the classical solution. So in principle, if we have infinite computing power, we can compute the cohomology and thereby determine the spectrum.
How do you know what the L0 is? The new L0? Or the weight? I guess you mean spectrum is a spectrum of scaling dimensions or masses or.
Yeah, I mean by spectrum I mean the set of physical states, and from the set of physical states I can then read off the masses in principle, right? Actually, at this point this is abstract. I will give you concrete computational methods in the next lecture, right? Because in the applications of specificity into the CFT, determining the spectrum, let's say for solutions corresponding to short RG flows, will correspond to determining the anomalous dimensions of the operators, right? So there is a concrete computational scheme how to extract these anomalous dimensions from the cohomology of the shifted BRST charge. Okay.
My point is that the cohomology is just a vector space.
Yes.
It doesn't have more structure, but there's the L0,
yes,
which is probably different.
I know. So okay.
It's okay.
Can you wait for the next lecture?
Yeah, sure.
I mean, it's a very nice algebraic procedure,
Yeah.
which was originally implemented by Ashoksen, and but it is I think you will appreciate it when I give you the details. Okay, but there is a computational scheme of how not to extract just the vector space, but also the let's say the eigenvalues of the L naught around the new background. Okay. So, but not only that. So, given that you can determine the spectrum of or the set of physical states, you can then compute the on-shell amplitude. So that should give you yet another set of observables, right, through the Feynman diagrams. Which you compute this with the Feynman rules given by this action S of 35. Of course, I mean, in principle, if you can compute these quantities, I mean, that would be good. But in general, I mean, extracting the on-shell amplitudes, even for the unshifted background from string field theory turns out to be hard, let alone for the shifted background. So you also need some simplest observables, which will be given by the simplest possible amplitudes which you can think of, and these would be the partition functions, where you don't have any external states inserted. So an example of such an amplitude would be precisely the on-shell value of the action, right? So that is supposed to be related, that is thought to be related to a shift of the worksheet partition function when going between the two backgrounds described either by the trivial perturbative solution phi equals 0 and the classical solution, right? So if for those two backgrounds we can compute a worksheet partition function, the shift in the partition function should be precisely measured by the on-shell value of the action. Now this statement is kind of still on a very experimental level of understanding in the case of the closed string. This on-shell value of the closed string action is supposed to be in some way related to the shift in the sphere partition function of the two backgrounds. While in the open string case, this statement is very, very solid, and it has been shown to work on many, many examples, precisely because, of the fact that in the open string field theory, since we have a simple formulation of the action, we can devise enough examples to actually test this statement and even to prove this statement. Yeah. So in the case of OSFT, we have this very, very simple observable, which is just the on-shell value of the action, and which measures the shift in the disk partition function between the old and the new background, which at the level of the worksheet CFT can be translated after a factor into a shift in what we call the G function of the boundary conformal field theory. Okay. So now, finally, I was about to give you an example of I would say the simplest class of solutions which we can construct in SFT, and these are the marginal deformations. But in view of time, I will probably not do that right now, and I will somehow try and subsume this example into the next lecture, where we talk about the applications into the CFT. So with that, I will just stop here.
Great, thanks. Questions?
Is there a proof that cubic closed string field theory does not exist, or?
Yeah, there is a paper by Barton Sweetback in which he gives a no-go theorem. I can give you a reference later. I think it's from the early 90s. So if you just look at the papers of Barton from that period, you should be able to find it.
So what doesn't exist? I didn't.
Oh, there's a no-go theorem for cubic closed string.
Ah, cubic. Yeah.
But there are certain. Okay, this no-go theorem has some assumptions, right? And so by violating these assumptions, you can perhaps also violate the no-go theorem, right? So for instance, if you start adding more and more fields into the game, some auxiliary fields, in particular, if you are able to add an infinite number of these, you should be able to build an example of a cubic closed string field theory. But that would kind of rob you of all the computational power, right? Because you would introduce an infinite number of rational degrees of freedom. So I guess the question is whether there is an example of a cubic closed string field theory with just a finite number of auxiliary fields added into the game. That's actually one of the research directions which is kind of active in today's community.
Can you maybe summarize once again? If you were to explain to a mathematician what is string field theory, then okay, we have this either L infinite or infinite algebra, but before that we need to have some vector space, right? And what structure do you need on the vector space? Like, for example, do you need this split into BC part and non-BC part, or can you just forget about that?
Yeah, I think if you want to make some contact between what you construct on the algebraic side and between some physics of some strings propagating on some space-time, I guess you have to assume that the Hilbert space has that particular structure, right? So otherwise, it is not clear that what you're computing is what you. Otherwise, it is not clear that what you have is really overcheat. Well, maybe what I've said is not entirely correct, actually. So for instance, that split into the matter and VC goes TFT is of course manifest at the level of the perturbative vacuum, which used to construct this SFT, right? But then when you expand around the solution in small fluctuations, right? And even though you know that in many cases what you found should be yet another consistent worksheet CFT background, it is no longer manifest at the level of the expansion action. How that would be split in the CFT matter of the new background and the BC go CFT, right? That action which you obtain here, that action expanded in small fluctuations, that is completely written in terms of the variables of the original worksheet CFT, in terms of the original matter and original BC ghost, right? So although that split is there, that is no longer the split of the new background, right? Yeah, and yeah, so and then again, as I was trying to emphasize in the first lecture, I mean, some of the solutions may not even correspond to the consistent string backgrounds, which would be obtainable from a worksheet CFT. Like,
plus BC.
Yeah, plus BC, right? I mean, you can, you can hope to find a solution to go string field theory, which would correspond to an NS5 brane, right? And yeah, the degrees of freedom of NS5 brane may not be, strings in the conventional sense, right? Right. So perhaps requiring the split into matter and BC ghost CFT may be too unnecessary.
Okay, so if we don't, but what do we need then? If we don't need that, do we we need a ghost number, or did we?
I guess we need some grading, right? Yeah, I mean that is an interesting question.
You just wanted to formulate some bootstrap problem, like to class, I guess.
Yes.
To classify
whatever string theory. I don't know if it's classifying string theories, classifying string backgrounds. I don't know. Just of course, it's very ambitious.
And it's yeah, indeed, it is, but it is an important question to ask. Yeah. Yeah, I think that also goes into the direction of obtaining a formulation of string field theory which would be manifestly background independent, right? I mean, the background independence here at this level of the SFT, of the form of the SFT which I was showing you, I mean, it should be there, right? Because at least to a very large extent, I should be able to obtain a very large class of consistent string backgrounds, from any starting consistent string background by constructing classical solution, right? So to a large extent, I mean, the action which I wrote down should be background independent, right? But that background independence is certainly not manifest because it is expressed in terms of variables which heavily depend on the choice of the background which I'm starting with, right? So perhaps what Dalemel is thinking about would be a good starting point of trying to formulate like manifested background independent action, something like Einstein-Hilbert action for gravity, right? That also doesn't depend on a particular classical solution around which you're expanding.
All right. Maybe let's thank Jakub again for a very nice lecture.